Let's work on the problem 5.3.26. Given the following circuit, find V naught using Thevenin's theorem. So the first step we need to get rid of this resistor associated with V naught. Take that out and we're going to call this as a VTH, and there's a plus and minus. So it is an open circuit, that portion. We can use Norton analysis or mesh analysis. So let's do the mesh analysis first. For the mesh analysis, we need to assign the mesh current. So we're going to call this as I sub 1 and this guy as I sub 2. There is another loop at the top. This one, we just want to call it as a 3 milli. We don't have to call it I sub 3. That mesh current is exactly the same as a 3 milliamp, because 3 milliamp, that independent current source is outer loop. So the mesh current in this case is the same. However, there's a 1 milliamp between two mesh currents. Therefore, we need to use super mesh. For mesh analysis, we need to do KVL using super mesh first. Then let's start with the 4K resistor first. So 4K times I sub 1, that's our reference current. And then the opposite direction, that is minus 3 milli. And then for the 12K, we have I sub 2 plus 2K, we have a I sub 2, and then minus 6 equals to 0. Simplify this expression in terms of I sub 1 and I sub 2. We have 4K I sub 1 plus 12K, 2K, 14K I sub 2. This is negative 12, negative 6, negative 18. Move it over, positive 18. And when we use mesh analysis with the super mesh, the second equation that we need to get is you need to do KCL, including that omitted the current source. So let's call it this is A. Now we can do KCL at node A. Then entering I sub 2 equals leaving I sub 1 plus 1 milli. So from here, I sub 1 minus I sub 2 equals to negative 1 milli. Now we have equation 1, equation 2. You can use your calculator, find the I sub 1 and I sub 2. Then we have I sub 1 as 2 over 9 and I sub 2 as 11 over 9. Now, in order to find the VTH from original circuit, we can do KVL in here. Now, we need to do the KVL. We need to find the voltage across here. Since this side is open circuit, all the current 3 milliamps go in this direction. Therefore, 3 milliamp times 2K, which is 6. The voltage across 12K, we can call it as a V of X. Then V of X equals 12K times I sub 2. And 12K times, what is I sub 2? We have 11 over 9 milli. Therefore, V of X is 132 over 9 volts. Now we are ready to find VTH. So when we do KVL with VTH, then we have a VTH minus Vx minus 6 equals to 0. Then VTH equals Vx plus 6. We say Vx is 132 over 9 plus 54 over 9, and that is 186 over 9. And we can divide top and bottom by 3, 62 over 3 volts. Also, we can use Norton analysis to find the VTH. If you want to find the VTH using Norton analysis, we need to identify the nodes first. So I'm going to call this node as a 6. I'll call this node as a V of A. I'm gonna call this node as a V of B. And then we need to assign the direction of the current. So there is a current going in that and 1 milliamp going into VA. We say another current going from VA to VB. And there's a fourth line here. And this is actually 3 milliamp. Right? Since this is open circuit, all the current going in here is gonna go down there. Let's do KCL at VA, that entering 6 minus VA over 4K, entering plus 1 milli, entering plus 3 milli equals leaving VA minus VB over 12K. So now we can multiply everywhere by 12K. Then this equation is going to be 18 minus 3VA plus, we have a 4 times 12, 48 equals VA minus VB. If we move this guy to the other side, we have a 66 equals 4VA minus VB. So that's our first equation. And we can get the second equation by doing KCL at VB. That is VA minus VB over 12K. That's entering. And we have a leaving current from here, VB, and downward. Then that is equal to VB over 2K. Again, we're going to multiply 12K for everywhere. Then VA minus VB equals 6VB. And we have a VA minus 7VB equals to 0. So that's our second equation. Now you can use your calculator to find VA and VB. VA is going to be 154 over 9 and VB is 22 over 9. Similar way, we're going to let this voltage across here, 12 kilo ohm resistor, we're going to call it as a VX. And we know there is a 6 volts here. Now, in order to find Vx, we need to do KVL. In this loop, we have a Vx plus Vb minus Va equals to 0. Why? Because when we let this as a Vb, we have Vb and plus minus. We say this is Va. We have a plus VA and minus. So the node A should follow the upper sign, just like what we did in here, plus 6 here. Then Vx equals Va minus Vb. That is 154 over 9 minus 22 over 9, which is 132 over 9. And that is 44 over 3. To find the VTH, we need to do one more KVL here. So this KVL is gonna be here. So negative 6 plus VTH minus Vx equals to 0. So VTH equals Vx plus 9 and Vx is 44 over 3 plus 9, that is 62 over 3 again. So we have a same answer. So it is similar difficulties. Either you use mesh analysis to find VTH or Norton analysis to find the VTH. Next step, we need to find RTH, looking at from here. In order to find the RTH, what we need to do, we need to make an open circuit for independent current sources and then short circuit for independent voltage source. If you redraw that, it looks like this. So when you work on the RTH, you should start combining these resistors far away from RTH. We cannot combine these two because they are not parallel, they are not series. However, this 4K and 2K, they are series, they share the same current. So we're going to combine them first. If we do, it's going to be 6K. Now, again, this 2K and 12K, they are not series, they are not parallel. Now this 12K and 6K, they are parallel. So we can combine them together. So if we do, we have multiply together and then add, that is 4K. So finally, our RTH equals to 6 kilo ohm. Thevenin VTH is 62 over 3 volts. And series RTH, that's the Thevenin circuit. Now, what did we remove from the original circuit to calculate VTH RTH? We remove 4 kilo ohm. So we need to put this back, and then we're going to call it as a V naught. That was a given. So now we can find V naught equals, we can use simply voltage division. 4K over sum of series resistors. 6K plus 4K, total supplying voltage 60 over 3. So that is 4 over 10 times 62 over 3. This is 5, this is 31. Therefore, V naught equals to 124 over 15 volts. Now, let's do the same problem using this time Norton theorem. For Thevenin, we need to take out the voltage that we need to find that out from the circuit, and we let that open circuit as a VTH. But for Norton's theorem, we need to make a short circuit. So instead of taking out and put it into VTH, what we're gonna do, we're gonna make it short circuit. So remove that and then make a short circuit, and we're gonna let current I sub n, the Norton current, always going downward. So let's use mesh analysis to analyze this circuit. And we're gonna assign the mesh current. This is gonna be I sub n, and this one and this one, I'm gonna call it I sub 1 and I sub 2. And this one is, we said 3 milli. Since the 1 milliamp independent current source is in between two mesh currents, I sub 1 and I sub 2, therefore we need to use super mesh. Super mesh is gonna be go outside. So KVL using super mesh. Then starting from 6 volts. So the current I sub 1 is entering negative terminal of the voltage source. So we're going to write it as negative 6 plus 4K. The top, our reference current is I sub 1 minus 3 milli. And then plus 12K. Our reference current is I sub 2 minus I sub n. And we have 2K just for I sub 2 equals to 0. Let's simplify this. So we have 4K I sub 1 and I sub 2, 12K and 2K plus 14K I sub 2 minus 12K I sub n. And we have negative 6 and negative 12, therefore equals to 18. So that's our first equation. Now we can do KVL using I sub n. Starting from this 2K, we have a 2K, our reference current this time, I sub n minus the opposite direction, 3 milli, and then plus 12K, we have I sub n minus the opposite direction, I sub 2. So from here, we have negative 12K I sub 2 plus 14 I sub n equals negative 6 in this side. So move it over, positive 6. So that's going to be our second equation. And we should have another one because we have 3 unknowns, I sub 1, I sub 2, and I sub n. Where we want to get the third one? Correct. So we have to use independent current source. So we're going to call it this as an A. Then this guy is I sub 2 and this guy is I sub 1. If we do KCL at node A, then we have entering I sub 2 equals leaving I sub 1 plus 1 milli. and that is I sub 1 minus I sub 2 equals -1. So that is our 3. So we have 3 equations and 3 unknowns. You use your calculator. We can find I sub 1 as 15 over 4, I sub 2 as 19 over 4, and I sub n equals 31 over 9. Now we found the I sub n, so we could put Norton's circuit always going upward. I sub n equals 31 over 9. RTH we found before as 6 kilo ohm, and that's it, right? And the missing resistor we took out to find the Norton current for this problem. If we put it back, that was a 4K, and that is V naught. So now we're gonna find the V naught. Before we find the V naught, we should find I sub naught first. So I sub naught equals, it's a simple current division, opposite 6K over sum of two parallel resistors, 6K plus 4K, times total supplying current, which is 31 over 9. That is 6 over 10 times 31 over 9. That is 31 over 15. Now V naught equals 4K times 31 over 15 milli. That is 124 over 15 volts. So in this problem, we use both Thevenin theorem and Norton theorem to find the V naught.